So this is the fifth session in the subject of signals and systems. And in this session, we are going to study the unit step signal and the unit ramp signal. This is what we are going to study. So let us start. We first start with the unit step signal, which is symbolically designated by UT. And graphically, it tells you the definition of UT. If you consider all negative times, right from 0 up to minus infinity, increasing in the negative direction, it remains 0. And if you consider all positive times, starting from 0 and going to infinity, it remains 1. And at t equal to 0, it jumps from 0 to 1. So this is of course the ideal definition of the ideal unit step signal. We shall see that physically it will not be possible for us to generate this perfectly, but we can come close to it. We'll see that. All right, this is the definition of the unit step signal. Now let us try to see physically how this signal will be generated. So we'll see a couple of examples. First example is very simple. Suppose you have a voltage source, a battery with a voltage V in series with the switch, and we take our output here. So as long as the switch is open, this V0 is going to be 0. And when the switch is closed, that is the instant we call as our t equal to 0. So immediately the voltage will jump to V. In that case, we can write V0 is equal to V times ut, because when ut has when you consider times which have negative values, ut is going to be 0. In that case, V0 will be 0. And if you consider times beyond 0 positive values, then V0 will be equal to V. And of course, if V is equal to 1 volt, not necessary, but if it is 1 volt, then V0 will be exactly the unit step function. So this is how it will look like. We have already seen. So this is t equal to 0 in this particular case is defined as the time at which the switch is closed and the voltage jumps to this value. So this is one physical way of generating a unit step, or in general a step voltage. For example, if this V has 5 volts, then here it will jump to 5. In that case, it's not unit step, but it will be 5 times ut. It's at least related to ut. All right. However, this is not the only way a step can occur. Let's see one more example. So set point also can be used as a step input. And let me give you a specific example of this. Consider the temperature control of an oven. Usually there will be a knob which will allow you to set the set point. For example, you might set the set point to, let's say, 20 degrees. Allow sufficient time to go by. In that case, the oven temperature will actually reach close to 20 degrees and remain constant. Now, suppose you suddenly turn the knob, let's say, to 80 degrees. Then you are generating a step in the set point input. So you can write the equation for the set point input. So in this fashion, set input will be 20 plus 60 ut. So let me repeat this. A control might change the set point from say 20 degrees to 80 degrees. In that case, the set input can be written as 20 plus 60 ut. So t equal to 0 is the time at which you suddenly change the knob. Okay. Before that, this is 0. So 20 degrees is the temperature. But after this, what happens? We want to see. So if you plot time versus the temperature of the oven, you find that at t equal to 0, it was 20 degrees. You suddenly provide a step input which takes it to 80 degrees, but the temperature doesn't immediately change. It takes a certain amount of time. So this not only tells you an alternative way in which the step input can be generated, but it also tells you something about how the step input is used. So in this case, you can see that the step input is used to measure the speed of response. If you have a temperature, if you have an oven with a higher speed of response, the curve will be sharper like this. And if it has a lower time response, it will be like this. So the step input can be used to measure the speed of response of a system. Although I have given the example of an oven here, but you can imagine large number of systems will respond in this fashion. So that is the application, one application of the step input. All right. Now we want to generate the step in the MATLAB program. Now before we do that, please note that a perfect unit step can neither be generated nor simulated. Okay. Even though, for example, in that battery with a switch we had shown, it looked as if we are generating a perfect step. But remember, wires also have certain resistance and capacitance. So if you consider a very short amount of time, interwiring capacitance may be quite small, but it will take a certain time before the output actually reaches that. So that is the case for any physical circuit or a system. So in a physical circuit or a system, you cannot have a perfect step. In simulator, can you have? In simulation also you cannot have, because you take any sample. There is no way in which the sample can have two values at the same time. See, step input, what happens? At t equal to 0, the value jumps from 0 to 1. And that is not possible even in a simulator. Also, the way the step is defined, we are assuming that right from minus infinity up to t equal to 0. So infinite time is not available. So when we do our simulation, of course, we assume certain time slice and then generate our unit step function. And as I said, infinite slope is not available. You cannot have any sample which has two values at the same time. That is not possible. So approximate generation is possible. All right. So let us see how to do this. So let us study now the MATLAB program to generate unit step signal. So these are, as usual, clear console, clear all the variables, clear figure. And now what we do is we provide the time vector with -4, 0, then 0.0001 and then 4. So let me explain. At t equal to -4, our output, which is stored in x, is equal to 0. At t equal to 0, it is still 0. Now in an ideal step, it jumps from 0 to 1, which is impossible for us to simulate. So what we do, we consider a very small increment of time in which it jumps to 1. So this increment of time can be as small as you wish. You can have empty number of zeros here. I have taken 0.0001. So what it means is at that t equal to 0, the output will be 0, and then it will jump to 1 at t equal to 0.0001 second. So for all practical purposes, it's very close to the ideal step. And then it remains 1 till 4. So remember, again, we are providing the endpoints for the straight lines, and the intermediate points have to be generated by using the piecewise linear function, which we had studied last time. So now we call the piecewise linear function. These are the outputs. This is the time array. This is the output array. PL, that is the function for the piecewise linear. And these are the inputs. So T array is input, X is input. And then what you can do, then you can just plot. So this again, as usual, we have studied this before. So we can now plot it by using all this. So if you wish, you can stop the video at this point and take a look at these details. We have already discussed these. So you will get an output something like this. Now if you look at this, it looks very close to an ideal signal, but actually it is from 0 to 1, it takes a little amount of time. In this case, we have set 0.0001 second. That is the way to approximate the unit step signal. If you want to make this approximation better, then you will have to reduce this time. So you can make 0.000001 and so on. Okay. So as far as the unit step is concerned, we have studied what is the definition of the unit step. We have seen how it is applied, what are the applications of unit step, mainly for studying the steady state error and the time response of systems. And now we have seen how to generate the unit step. So next, we will study the ramp function. But before that, this PL function, that is piecewise linear function, which we had studied in the last session, I have just kept it here for your reference. And note that in this particular case, I have changed the time slice somewhat. By instead of dividing by 100, I have divided by 1000. Remember, larger this number is, smaller will be TS and better will be your approximation. So that is what I have done in this case. All right. Let us now define the ramp input. So its symbol is RT. And what's the definition? This graph tells you the definition. For all negative values of time, it remains 0. And for positive values of time, it increases with a unit slope. Note this, at 0 it is 0, t equal to 1 second, it has amplitude 1, 2 seconds, amplitude 2, 3, 3, 4 seconds, the amplitude is 4. In short, it's a straight line with a unit slope. Okay, so this is the definition of the unit ramp signal. Now the question is how to generate this. So the generation of the ramp, again, clear console, clear, and then clear figure. Now we need 3 points. Remember, let me show that again to you. As I said, we can't have infinite time, so we are going to simulate this over -4 second to +4 second. So you have one starting point here, and the straight line ends here. So this is 1, 2, and this is the third point, which of course means that you will have 2 lines. All right. So we have 3 points, as I said, t equal to -4, x is equal to 0, t equal to 0, this is 0, and then it increases linearly up to 4. So at 4 seconds, it reaches the amplitude of 4. All right. So now what you do, you call the piecewise linear function, generate the output y ty, and again plot it as usual. So then it will look like this. So you can see it's 0 from -4 up to 0, and then it increases linearly until it reaches the value of 4 at t equal to 4. All right. So what we have done, we have defined what is a ramp signal, and we have seen how to generate it by using MATLAB program. Now what we want to do is to study what is the application of this. So use of ramp signals. So this is often used to test systems which are required to respond to continuously changing signal. Okay. Remember, our step input, it changed only once. It jumped from 0 to 1 at t equal to 0, and then it remained constant. And all the system had to do was to catch up with it. However, there are times when your input keeps on changing constantly with respect to time. In that case, at whatever rate it is changing, the system must respond at that rate. So that is where the testing of these systems by ramp input is useful. You provide a ramp and see whether the output is also changing with that slope or not. So whether rate of change of output follows that of input, you can test that. For example, so let me give you a couple of examples here. An antenna tracking a satellite. If you consider a non-geostationary satellite, then you find that the antenna is not facing the satellite all the time, since the satellite moves. So as it moves, the antenna must track, and you must track at the appropriate speed. So as I said, let me repeat that for non-geostationary satellite rotating in the sky, the receiving antenna orientation must change continuously to receive good strength of the signal. This is one application where the system can be tested by a ramp signal. Another one is a ramp command to an aeroplane system to change pitch as a function of time. As the aeroplane takes off, the pitch needs to change as a function of time. So that is another example of a signal where the system can be tested by the use of ramp. So in this particular session, we have studied the unit step, what is its definition, what is its application, how to generate it in the MATLAB, and we have also studied what is a unit ramp, how to generate it in the MATLAB, and what are the applications of the unit ramp. And that is all in this session.